Hello everyone, we are group FT33. Today we are presenting our AI project, which is spam email detector. My name is Kim Bo-kyung and with my teammates Topi Yang, Jiajie, Emerald, and Harsha. We are sharing how our model detects and filters spam emails effectively using AI. This is our presentation outline. First, we'll start with project statement and objectives, followed by dataset, methodology, models and results, demo and implementation, and finally our conclusions. I'm presenting project statement and objectives. These days, unwanted spam emails pose security threats such as phishing, malware, and reducing productivity, affecting individuals and organizations. Our main objective is to automate the classification of spam and ham emails using machine learning. We compare three different models to identify which one performs best in terms of accuracy, precision, and recall. This helps us determine the most effective approach for real-world email filtering.
Now, I will talk about the methodology we use to tackle the problem statement. Firstly, data preparation. This involves loading our initial dataset and separating the feature set from the target label. Next, feature scaling. Here, we apply the max ABS scaler specifically to normalize our word frequencies. This crucial step prevents any single feature from dominating the learning process. From there, the data is split in an 80-20 train test split while also utilizing stratified sampling to actively maintain the original distribution of our target labels across both training and testing sets. Finally, training and evaluation. The model is trained on the 80% training set and evaluated the performance on the unseen 20% test set, utilizing detailed metrics like accuracy, precision, recall, and the F1 score for a comprehensive classification report.
So now let's take a look at the three chosen models. We evaluated three machine learning models for spam detection: multinomial naive Bayes, logistic regression, and support vector machine, each using a distinct mathematical approach. Naive Bayes is a probability-based model that calculates the likelihood of an email being spam based on the probabilities of individual words, assuming all words are independent. This simplification makes it extremely fast but less nuanced. Logistic regression, on the other hand, is a statistical model that assigns weights to words and applies the sigmoid function to produce a probability between 0 and 1, giving us an interpretable confidence score for each prediction. Lastly, we have support vector machine, which takes a geometric approach by mapping emails as points in high-dimensional space and finding the best separating boundary known as the hyperplane that maximizes the margin between spam and non-spam, which is ham. These three models together represent probabilistic, statistical, and geometric methods for classification. When comparing the three, Taipei stands out for simplicity and speed, making it ideal for real-time filtering, though it's limited by its dependence assumption. Logistic regression offers a good balance between interpretability and accuracy that performs best when classes are linearly separable. Last but not least, we have SVM, which delivers the highest precision, especially in complex and high-dimensional data sets, but at the cost of greater computational demand and reduced interpretability. Overall, these theoretical trade-offs helped guide our expectation for real-world performance of these three models.
I'd like to present the dataset overview and how we implement the models. Our project used the preprocessed enron image dataset, which contains 5,172 emails. Each email is already converted into a bag of words format, meaning instead of raw text, each email is represented by 3,000 numerical features, where each column corresponds to a specific word and its frequency. For example, the columns for words like the, to, you, and n. The final column is our target label, where 0 represent ham and 1 represent span. This will pre-factorize dataset save us from doing manual test cleaning, tokenization, or factorization, so we can focus directly on model training. First, we separated the dataset into feature A's and label Y. We also normalized the labels so that all ham entry became a 0 and all span entry became 1, ensuring consistency across models. Then we applied the mass F scaler with scale all value between -1 and 1 without making any negative, ideal for frequency-based features. This keeps the input balance for models like logistic regression and naive Bayes. Finally, we perform on 80-20 train test split using stratify equal to y. That means 80% of the emails were used for training and 20% for testing, while preserving the same span to ham ratio across both sets, ensuring a fair evaluation. So we implemented three baseline models using scikit-learn. For model one, multinomial naive, this model assumed that on what frequency follow a multinomial distribution. We use multinomial NP alpha equal to 1.0 and fitted it with our training data. It calculates conditional probability, for example, how likely a message is spam given that it will contain word like free or winner. The model is simple, fast, and perform well for test classification problem. Then for model 2 logistic regression, here we use logistic regression with the Saga solver, Penalty 12, and Mass Ether 5000. This model learns a way for every word feature, predict the probability of an email being spammed using the sigmoid function. During training, it adjusts this way to minimize classification errors. After fitting, we use predict and classification report to generate metrics like accuracy, precision, recall, and advanced score. For Model 3 linear SVM, the linear SVM model focuses on finding the optimal hyperplanes that best separate span from ham-even. It doesn't work with probability, but instead maximize the margin between the two classes. We use the one and random state 42 for stability. This model is especially good for high-dimensional sparse dataset like ours, where there are many features but relatively few non-zero values. To make our experiment more realistic, we tested the robustness of each model by simulating noisy data. We created two helper functions, drop was randomly is set some was counts to 0 to mimic missing tokens, while add noise function adds small random integers to stimulate a dipoles or extra word. Then we evaluated all models again under this noisy condition to see how well they could handle imperfect real-world inputs. This step helped us understand which model remain consistent even when the data isn't perfectly clean. To summarize, we loaded and prepared the dataset, scaled the features, split the data, trained three machine learning models, and tested them under noise. This consistent process ensured that each model was compared fairly and that our results reflect real-world image filtering performance.
So now talking about the model performances, all three models perform pretty well, but there are some differences that tells us about their real-world usefulness. So naive Bayes gave us a 92% accuracy, which is pretty good. It tells us 92% of the time is correct in predicting hand spam. But when talking about the precision recall, which is the false positive and false negative cases, it doesn't do as well, actually much worse compared to linear regression and linear SPF. For the two linear classifiers, both are at 97% accuracy, which is very good. But logistic regression is slightly more careful, does higher precision, but lets more spam through, which is 94% lower than SPM. So SPM will be the opposite, blocking more spam, but making more mistakes in the way. We will talk about F1 score later in the robustness test. So for the confusion matrix, it tells us the true positive, true negative, false negative cases. So top left would be true negative case where legitimate emails are considered legit. Top right would be false positive cases where legitimate emails are considered as spam emails. Bottom left would be false negative cases where spam emails are considered as legit emails. Then bottom right would have to be true positive cases where spam is classified as spam. This complements what we know from the previous results where naive Bayes just lets a lot more spam through as either true positive and true negative cases. But for the two linear models, similarly with just now, logistic regression allows less false positive cases, thus only 13 compared to 22, but catches a lot less spam, which is why it's 18. Then SPM catches much more spam emails, but makes much more mistakes putting ham email in spam in class. So now talking about the robustness of each, we are using some real-world simulations that will contain missing words and noisy data in order to bleed through into the inbox. So when we randomly remove 10% of the words, all models still held up pretty well, thus telling us that they don't overly rely on specific keywords. However, with just 5% noise, which can include typos or corruption. All models to dip in the accuracy front and also F1 front, but we'll talk about accuracy at the moment. So the linear models were also dropping significantly, still held up their basic structure, showing that they are learning deeper patterns rather than just word frequencies. Naive bias, on the other hand, drops to a 0.55%, which is essentially random charts. And when we combine with the 10% missing words, it drops to a 0.5%, which is a literal coin toss. However, talking about F1 score, F1 score is the harmonic mean between precision and recall, thus the average of false positive and false negative cases. So high F1 score would mean there's a lower amount of true positive and true negative cases, while low F1 score means it's just letting a lot of spam emails, ham emails, while also blocking a lot of legitimate emails. In the additive noise test, naive bias surprisingly held up pretty well, but when comparing to the accuracy part, it still just means that it's random chance. So the F1 score in this case isn't really that reliable. However, for logistic regression and linear SPM, both dropped to a 0.2%, which tells us essentially that they lost their discrimination ability once noise is added. Once noise is added, they are making much more mistakes.
Next is our insight, gain, and conclusions. From our experiments, night base was the fastest but less accurate due to its independence assumption. Logistic regression showed high precision at 96%, while SPM achieved the best recall at 98%. For spam detection, recall is more important, so it's better to catch all spam even if some normal emails are flagged. Overall, the linear SVM performed the best with 97.2% accuracy and production-ready reliability. In the future, we plan to explore deep learning models like LSTMs or transformers to capture more complex word relationships. That's all for our presentation. Thanks for listening, everyone.